Hello and welcome to Lab 2 of the Bayesian Machine Learning module of the FMML course. In this lab, we are going to learn about the naive Bayes classifier, which is an application of the Bayes rule to classification problems. First, we'll be looking at an analytical example set where we are taking a real valued feature input and trying to perform binary classification on it. We'll see how in different ways we can incorporate our prior knowledge about the world to change the way these decisions are made. Next, we will try to apply this Bayesian machine learning to a discrete valued input in the context of a real world example of healthcare, and we'll see how naive Bayes classifiers perform in classifying the disease given the symptoms. So let's get started by downloading the datasets that we have hosted on our public GitHub repo and importing the libraries. The first challenge that we are trying to analyze at the moment analytically without any code is how do we handle the problem of class imbalance in classifiers? So we have seen in the previous chapters that there might be a data imbalance across the two classes that we are trying to classify over. You may have 1 million examples of a dog and you may just have a few 100,000 examples of a cat. And given such data, the neural network can learn to exploit this to guess that the image is a dog whenever it is confused. We need to solve this problem. And to solve this problem, we need to incorporate the fact that we know that probability of dog is equal to probability of cat. And this is what we might try to do with the application of priors. We can say that the prior probability of image being that of a dog is 50% and that of a cat is also 50%. Similarly, we may have the opposite problem of having balanced data, say of dogs and of wolves, but we are trying to have a image ID system for a city, and we know that in cities, the probability of seeing a wolf is much lower than seeing a dog. So whenever we have confusion, we should probably err on the side of guessing that it is a dog than guessing that it is a wolf. And therefore, if you have such an image ID system or a species counting system deployed in a city, maybe you want to incorporate the fact that the probability of the image being a dog is 90% and that of it being a wolf is just 10%. So here we take a look at a real valued feature example. And in this case, we have one class, the red class, which is 10 times more probable with 10 times more number of examples than the blue class. We know that this probability density is representative of the ground truth and not just an artifact of the data set that we have generated. So it is in reality that the red class is more probable than the blue class. In such a case, what we have done is we have made a feature distribution between -1 and +2, and the mean of the red class is at 0 and the mean of the blue class is at 1. And you would guess that the boundary that should separate them is the boundary at 0.5, the line in black right down at the center. However, since the red class is a lot more probable, even though at 0.5 the probability fall off of each of both the red classes and blue classes are nearly equal, since the inherent probability of any point being in the red class is much higher, all of the points here, most of the points that occur at 0.5 actually belong to the red class. And therefore, because we know that we have the prior probability of the red class being significantly higher, we need to shift our decision boundary to the one that we have shown over here in the green line. At this green line, you notice that the red histograms, which is the probability of any class or the number of examples for which the class was red, is nearly equal to this height of the blue histograms. If we did not have representative number of examples and we just knew this prior probability that red is 10 times more likely than blue, but we had equal number of examples, we could still have used this prior information to shift out the decision boundary, pushing it to the green line over here. This is akin to our example of the dogs and the wolves that we just discussed. Next, we'll be trying to take a look at places where the number of examples is actually uniformly distributed. So both of the classes are equiprobable, and yet we have some prior information. We have the prior information that the blue class has more variance than the red class, even though the means of both of the classes are exactly at the previous position, and both of these classes have exactly 10,000 examples drawn from them. So whenever we have such an information, we notice that the height of the red rectangles are equal to the height of the blue rectangles a little to the left of the 0.5 line. And therefore, the decision boundary must shift to the left. This is because any point at 0.5 is equally an outlier for the red class and for the blue class. But since blue class is more likely to have outliers, if you want to attribute this outlier to someone, you would much rather attribute it to the blue class than to the red class. So it's not always the probability of the classes being known, but it's also sometimes that whenever you have a class which has more variance in it, you are more likely to prefer judging that class whenever you have an outlier which seems to be equally far away from both of the classes. Next, such analysis can help us change the way we design our models. So here we take a look at some more data, and this data over here has the red class distributed around its mean of 0.0 and has a reasonably low variance. However, the blue class is again distributed around its mean of 1.0 but has a very high variance. What ends up happening is that all of the outlier points to the extreme left also belong to the blue class, and everything on the right belongs to the blue class, and only the points in the center belong to the red class. This analysis of the prior probabilities tells us that since the variance of the blue class is high enough, the type of classifier we should use is not a single decision boundary classifier like logistic regression or linear regression, which on a single layer. Rather, we should try to either construct features which would allow these sorts of regressions to work, or we should use a decision tree classifier with multiple boundaries. The number of splits that you want to make would be very much dependent on the prior knowledge of the distributions that you have about the two classes. While having such knowledge about these distributions is hard for complicated data types like images and such, this sort of analysis is extremely useful for several industrial problems. You may have, say, engine features to figure out some outlier detection on plane engines, on other types of machinery, and Bayesian machine learning has a lot of application on engineering problems of this kind. Next, we move on to the application of Bayes classifiers to healthcare. Here we'll be taking a look at a dataset downloaded from Kaggle. You can search it directly on the Kaggle datasets page, and you can try to find other datasets which are similar to it. We have modified the dataset a little. So we have the training symptoms and the test symptoms. So let me try to display the CSV files. We have this CSV file here, and we have a bunch of different examples of which are the symptoms that a person is suffering from. So irregular sugar level, lethargy, and so on are the symptoms. And let's move over to the right, and we have the prognosis. So if a person has fungal infections or different kinds of diseases, so tuberculosis, diarrhea, etc., all of these diseases are documented in this dataset. We have a similar dataset in symptoms test.csv, but we only have the we are only supposed to use the features, not the prognosis for that dataset. So we are trying to deal with the problem of if a person has a couple of symptoms, the symptoms being fatigue and vomiting, then what kind of disease does the person have? So we'll take a look at how a person would go along analyzing this disease problem. And since the independent symptoms are discrete valued inputs, this is an example of a multi-class classification problem on discrete inputs. So first we load the dataset and we render the dataset much like an Excel spreadsheet. And the first thing that we should try to do, given the fact that we have a distribution of outputs, a multi-class distribution of outputs, given a bunch of Boolean inputs, we can try to plot a heat map of the diseases. So here we see all of the different diseases: dengue, typhoid, hepatitis A, B, C, and so on. And over here at the bottom, we see the different symptoms: lethargy and fatigue and others would be right over here. And each of the blocks are white most in color if there are multiple examples corresponding to those, and they are blue in color if there are no examples of such. So as you would see that this sort of data set is pretty sparse and we do not have a large number of examples, but we'll still try to reason with this. Bayesian machine learning algorithms are pretty good at trying to reason even in data sparsity, although it would always help to have more data to ensure that things that are being ruled out for a reason. So the first thing that we do after getting the full joint distribution over all of the features and all of the possible outputs is that we try to compute the marginal distributions. The marginal distributions means that what is the probability of having any disease and what is the probability of having any symptom. So on these plots, we notice that the probability of having common cold is extremely high. Common cold is the most probable disease, and many people in their home diagnosis would just say that if you have vomiting and if you have lethargy and fever, then it's probably just common cold. However, there are other diseases like tuberculosis and hepatitis and dengue, which are still in the running here. Next, let's take a look at the symptoms probability. So in symptoms probability, we have weight gain and burning mixtures. Okay, I don't know that. These being highly probable. And then we have some of our other symptoms. Let's try to find them. So wherever they are, those symptoms of lethargy, and these would be there, and they would have some probability associated with them, which we'll be using for our application of the Bayes rule. So we try to perform some symptom level research, and this is sort of the online lookup that we do. When we take a look at vomiting and fatigue being our symptoms, we can see what are the diseases that are associated with it. So diseases like GERD, which is gastroesophageal reflux disorder, is associated with vomiting and not with fatigue. So we can rule this out, and we can rule out a bunch of other examples. But there are a few examples here like dengue and typhoid, which have both of the symptoms being shown. So if you just try to reason based on online searches, you would come up with these examples: dengue, typhoid, etc., being the most probable explanations for your disease. So let's take a look at the plot of the combined evidence. The probability because of vomiting times the probability because of fatigue has been combined into this single bar chart. And in the single bar chart, we see that diseases like tuberculosis, hypoglycemia, typhoid, dengue, etc. have high probabilities. I think typhoid has the highest probability of them all, and common cold has a pretty low probability. So we have seen that if we just try to reason based on our common knowledge, we'll come up with the diagnosis as common cold. Whereas if we just try to reason based on the probabilities of those symptoms, trying to match the symptoms online, then we might come up with the idea of it being typhoid. However, we know for a fact that diseases like dengue, typhoid, etc. may not occur in the city as much because they had low prior values. And therefore, what a good doctor does, and how our medical reasoning systems should try to think, is they should try to combine the evidence and the prior and the likelihood together to form the posterior distribution. So here we have used the application of Bayes rule. We have computed the evidence and we knew the priors, which were defined above, and we have tried to compute the posterior, or value proportional to the posterior, in the same way we talked about in the previous lab, that computing the posterior, dividing and normalizing the posterior by the denominator is often computationally expensive, so we have avoided that. And since we just want a value proportional to the posterior and we do not care about normalization of probabilities to 1, we have plotted these posteriors. And here you can see that tuberculosis has the highest posterior value because it was also a common disease and one that matched the symptoms, whereas other diseases like hepatitis and dengue have fallen off because of their inherent probability, and common cold has also fallen off because of its poor symptom matching nature. So this is how we would reason about multi-class classification, by computing for every single class, the probability of class given the symptoms, which would be equal to the probability of symptoms given the class times the probability of the class divided by the probability of the symptoms. The probability of symptoms can be ignored because it's just a normalization factor, and if you have more than one symptoms, then you can just multiply the probability of those symptoms together to apply it to the Bayes rule. So the take-home lesson here is that when we are trying to reason over data which may be of a sparse nature, or where we may need to incorporate our previous knowledge to be sufficient to make it sufficient to reason about real world problems, then using Bayesian machine learning models is a great idea. Bayesian machine learning models do not work well where there is insane amounts of data and it's extremely complicatedly modeled with functions. So image data and others are poorly handled by Bayesian machine learning. But when you have categorical inputs, when you have Boolean values of whether or not there is a particular symptom for a person, then the ideas of Bayes rule work out pretty well. There are a large number of videos that have been used to visualize these things, and 3Blue, 1Brown, and Veritasium both have amazing visualizations for all of these concepts. And they have also shown the example that we discussed in the previous lab, which was the librarian versus farmer problem, as well as the medical knowledge problem in all of these 5 videos linked over here. So please do take a look, and thank you so much for listening. Bye bye.